A couple more minutes to go. That's good. All right. Good afternoon. Let's see. A couple of things. Number one, I think any one of you had problems with enrollment. That should be all resolved. I looked at the list recently. It seemed like everybody got enrolled now, so that's done. A couple of other either small issues before we go. So discussion sessions. Today we're going to have the first discussion session, right there at I think it's 5 o'clock, right here in this room. So it's going to be videotaped. Again, if you cannot make it, you can watch it. You can broadcast it, podcast it, the whole thing. Hours of the TAs. I haven't announced. All the office hours of different TAs will be also where the labs are being held. That's 353 Corey. Now, I sent Loretta Lutcher in 253 Corey the list just before class. I sent her the list of the class list. So I think starting tomorrow, you can go to 253 Corey Hall and get your card key programmed for entrance into the lab space, which is 353. Okay. Let's see what else that's important. So we're going to have the first lab next week. We're going to starting on Tuesday or Monday. We also have a homework. Homework number 1 is due this Friday, and there's a little change here. I was a little bit confused. It happens at my age. I was telling you to drop off the homework in 253 Corey. Actually, there's a better solution. In 240 Corey, which is this this kind of a communal space, just when you go into Corey, where the student space, where you have, when you go to the courtyard in the middle of the building, there's a bunch of boxes there where you can drop off homeworks, and there's going to be a box in there, 141, and you just drop it in there, perfectly secure, and that allows you to go till 5 o'clock. So I give you an extra half hour again. Yes, Mike. It's changed? Yeah. Because I just sent a message out that we did it in 353, but anyhow. Oh well. Let's, where's that? What room is that? Yeah, so we'll check. I think 353 is kind of nicer, but there might be laps at the same time going on there. But it's a nicer place because it has projection capabilities, broader spaces, more computers. 382, as far as I recall, is one of those tiny little kind of holes in the wall type of things. So we'll figure it out. Okay, I'll check it out. I'll confirm this. We're going to get second homework on Friday. It's going to talk about basic, also some more kind of more extensive drilling on transistor models. We're going to start doing some transistor analysis. As I mentioned, this class we're going to use 90 nanometers like you do in the homework. So we're going to look at some of the characteristics of a 90 nanometer transistor and how it's going to impact design in this space. And you will see there's some differentiation. If you look at the textbook, it's 250 nanometers, or 90 nanometers. Those transistors look somewhat the same, but they're somewhat different too, as you will notice. When you make things smaller, certain things happen. And these are definitely get more spoken in the 90 nanometer space. Any questions? Issues that need to be resolved? There was one thing, I'm just trying to think about this. There was one more request that somebody had emailed me about a half-hour difference somewhere. Oh, related. It's a midterm too. Who's taking 122? So I know there's a number of you taking 122, and 122 has a class which is 5:30 to 7 or something like that on Wednesday. And remember, we had second midterm planned 6:30 till 8. What I'm probably going to do for those of you who take 122, we're just going to move the midterm 1.5 hours later. So we're going to start at 7 till 8:30. That avoids the overlap with those of you who take 122. So that's something we easily can still adjust and accommodate those of you. So that's the only other thing that basically popped up in my mind. Okay, good. All right, so I'm going to talk a little bit more about metrics. We're not done yet completely. And then what I'm going to do is, what the heck, right? Even without knowing what a transistor is, we're going to start designing an inverter. And see and look at somehow some of those metrics apply to a simple CMOS inverter. And then what I would like to do towards the end of the lecture is say, well, gee, let's now assume that our transistors are not as good anymore as they used to be. Let's assume that we have some more advanced features popping in. How will that impact some of our metrics? This is very first order, but at least gives you a first glance of the type of things we're looking at in this class. So let me review what I discussed last class. Reliability, we talked about area and cost, right? How they're related to each other. And then we talked about reliability. How do you measure reliability in a digital gate? And as you mentioned for an inverter, we look at something which is called the voltage transfer characteristic, which plots V in as a function of V out. And what you get is somewhere a curve like this with a output level which is called VOH, that's the high level, and a VOL. Okay, these are my nominal voltage levels. Now, as I mentioned, reliability is measured by how much noise I can sustain before the system goes kind of haywire. Right? How can we measure that? And that's done through a set of secondary measures. So while you look at the voltage transfer characteristic, we know that for a real digital gate, we have to have in the middle a gain which is larger than 1. Actually, minus 1, because it's a negative gain. Right? It's an inverter, after all. So the gain here in the middle area is going to be larger than minus 1, which means that there's some points here where the gain is equal to minus 1. We look at those points and we call them VIL and VIH. And then, so by the way, this was VOL. So the noise margins are going to be determined by the difference I have at the lower side between the value of VOL, typically 0 volt, and VIL. This here is my noise margin low. And on the other side, I have VOH here. This should be H. And I have my noise margin high. And you can imagine that you would like to have those things as large as possible. Now, if I put, there's one more parameter I want to bring up here. If I take the 45-degree lines and I cross where I call this curve here, we call this VM, or this is switching threshold of the gate. Okay? For an ideal symmetrical gate, I would like to have VM sitting in the middle between 0 and the high level, or VDD. So you position this smack in the middle of your type of curve. And so typically, I would like to see this at VDD over 2. Now, you can imagine that if I would have an ideal gate, when the gain is really high, this curve will basically migrate to something which looks like this. Right, this is infinite gain in the midpoint. In that case, if I put VM in the middle, I will have noise margins which is equal to VDD over 2 and VDD over 2. These are the maximum noise margins I can get. And that determines what I would call the ideal digital gate. Okay? So that's what we're trying to strive at. And as we'll see, the good news is that your ordinary CMOS inverter actually gets darn close to this. It's pretty amazing. Two PMOS inverter and NMOS, PMOS transistor, NMOS transistor on top of each other. And I get a VTC, a voltage transfer characteristic, which is darn close to my ideal curve. Which why is this gate has been so popular for the last 30 years. It's been used in most of the designs. The majority of designs use this because it's a darn robust gate. Okay? Okay, so that's reliability. At the end of the class, I briefly introduced some other properties, your propagation delay. And the propagation delay is determined as the time difference between, if I look at my input waveform to an inverter, so you have here V in, this is V out. I apply a step at the input. I measure the 50% point at where the 50% point happens in the time of this input. And a little bit later, this output will go low. We look at the 50% point of that, and we measure the difference between the two. Okay, so you have your input waveform. It goes up. The output goes down a little bit later. And you look at the midpoints. That's going to define my what we call the TP, propagation delay from high to low. Obviously, there's a high to low transition at the output. Similarly, I can do the same thing at the other direction, where I get TPLH, low to high. And our overall average propagation delay is going to be, as it says, the average between the two. It's TPLH plus TPHL over 2. Okay? So that's our time delay definitions. So let's try to apply this. Oh, by the way, before I go and try to compute this for a very simple structure, let me mention one thing, which is important. Number one, if I look at the delay here, you can see that I assume that the input waveform has a certain, what we call, slope. It's not a step function. Step functions don't exist in the ideal world. You're always going to have some finite slope. And the output is also going to have a finite slope. We call it the rise time and the fall time. Now you might imagine that the propagation delay of a gate is going to be somewhat of a function of the rise and the fall time of the input. If I make a very slow moving input, there's a chance that your propagation delay is going to be a little bit larger. If I make something which is really fast, your propagation delay is going to be smaller. So remember, propagation delay is going to be a function of the rise and the fall times of the input waveforms. Okay, that's an important one. Now you can also imagine that if I take this inverter here, the propagation delay of this single inverter somewhat is going to be determined by what I add at the output. If I, for instance, add here a giant capacitor, huge, big capacitor, you can imagine that this gate is going to take a while to charge up that capacitor. So it's going to get slower. So you might imagine that the delay of a gate is going to be determined by the fan-out, as we defined last class, the number of gates I connect at the output. Right? The more I connect to the output, the slower my gate will become, because it has to work harder to drive that capacitance. Okay? So that's important. So now the question is, how do you define propagation delay of a gate? Because it's a function of rise and fall times, and it's a function of your fan out, right? So it's going to be a variable. There's a couple of things we do. Actually, for a reason which I don't want to explain right now, but will become apparent in about 6-7 lectures or something like that. It turns out that people like to have an inverter driving 4 inverters. If you would choose your fan out, right, how would you choose it? How many gates would you like to have? Turns out that designers seem to be liking 4 inverters, 1 inverter driving 4. Actually, it turns out that driving 4 inverters is actually an optimal number. So this is the standard situation. So if I'm asking you, give me the propagation delay of a gate, and you go into SPICE, don't ever do this. Right? You take an inverter, and you append nothing at the output. You can imagine this thing is going to be fast, really fast. It's going to go, pew. But it's unrealistic, right? Because it's pretty useless to have driving nothing. So typically what we're going to do in simulations is we're going to simulate a pattern like this. We're going to connect 4 inverters at the output as a typical load. So we standardize the definition of delay to the Fanout of 4 delay. Okay? And again, we'll see later why 4 is a magical number. Actually, it should be 3.6, but 4 is close enough. It's kind of hard to drive 3.6 inverters. Right? So we'll talk about that later. So this is an important thing to remember. You basically take 4 inverters typically when you have to do simulation. Okay. Having said that, let's do a little example. Here's a very simple circuit, an RC network. As you remember from E40, this is described by a single differential equation, first order differential equation, something you still can solve by hand. All the other stuff, it gets quickly more complex if you have more resistors and capacitors. But this thing is something we know how to describe, right? You can write down Kirchhoff's law for this node, which says that C times dV out dt plus R times V out minus VDD is equal to 0. Done. Right? That's the differential equation describing the transient performance of this gate. Now suppose I apply an input step here. Right? So you have your input. I apply a step at the input. What's going to happen? Initially my capacitance is at 0. And then obviously I apply a step. You can see that through this resistor we'll charge up the capacitor. Right? So you will get a waveform that starts at 0. The output will be somewhere at 0. And we'll go to VDD eventually. If the step that I'm applying is equal to VDD. Right? Now, from E40, you probably know that the waveform you're going to see is something like this. We're going to charge up this capacitor, and then exponentially, asymptotically, we basically will be approaching VDD. Very simple network, first order, single time constant network. Okay? So if you like differential equations, you can solve them by hand, or you can take MATLAB or something like that. They solve differential equations for you as well. You want to, but if you solve this equation, you basically come up with this answer. V out of this structure is going to be equal to V, which is your voltage step, times 1 minus e to the power t over tau. And tau is a time constant. Tau is equal to RC. Okay? So we'll see that we will have an exponential approaching VDD, and the time constant of that exponential is tau. Okay? Now, if I want to compute the propagation delay of this gate, let's assume that this is a gate. I want to compute the propagation delay of this gate. So I have a step function at the input, and the output is going to go asymptotically to VDD. The propagation delay is going to be the difference between the 50% points at the input and the output. So what I have to find out, to find the propagation delay of this structure, I take the middle point. Here it is. That's VDD over 2, and I find out how much time it takes to get there. I can easily do that by plugging into this equation here. I say this has to be equal to VDD over 2. If this is VDD, what is T? That basically gets it there. You just solve that. And the answer is beautiful. It comes out quite nicely. You solve this thing, and you find that the propagation delay of this structure is going to be equal to tau, the time constant of my network, the RC, times logarithm over 2, natural logarithm 2. Very important number. I think you have to remember this. You look at this number, and you're going to have to remember it for the rest of the semester, because we're going to use it over and over again. Actually, ln2 is equal to 0.69. If you want to be a little bit less accurate, 0.7 approximately. So what we see is that you have a single RC network. Its propagation delay, as defined by the 50-50% point, is 70% of the time constant of that network. Okay? Now, you say that's kind of interesting, but why should I learn about this? Why do I care about RC networks? Well, if I look at a CMOS inverter, with a PMOS, NMOS, and an NMOS network, actually, it's nothing else than a first order. When you look at the transient behavior of that network, it's nothing else than a first order RC network. So if you know this R, if you have an inverter, and I know R and I know C, I know the propagation delay. It's 0.69 times C. I don't even have to solve the differential equation. I know by heart. And we're going to use this over and over and over again. It's a very simple way for me to compute propagation delays of networks. Okay? Good. So that's propagation delay. One last metric, and then I go and apply some of those things to a real inverter. Okay? I haven't talked about power yet. Well, we did. First lecture, I mentioned to you that power is a big issue. Power is a big concern from a design perspective. Now, what do I mean by power? Actually, if you look at a chip and you measure power dissipation, how would you measure it? Well, there's a couple of different things I can measure. Right? I take my chip and I apply a supply thingy here. Somewhere I have a supply box which applies a certain voltage, and I can look at the current flowing out of that supply box. I could have a measurement on an oscilloscope or something like that that measures the current flowing out of the supply. Okay? So the thing you will observe when the thing is just running, you will see that the power dissipation of this chip is going to be a function of time. It will be variable. And it's equal to the supply voltage I'm applying, VT, which is maybe a variable, and the current that goes into the network. That's the definition of power, right? V times I. Now, V should be a constant, presumably. So this is equal to V supply. So the instantaneous power dissipation of your network is going to be the supply voltage times the current that I'm drawing from the supply, which is a variable. If I'm looking at actually a fairly complex digital chip, you will see that the current of your network that you're basically going to take out of supply is going to be more looking like this, and then doing this again, and then doing this again. You will see actually big spikes in power dissipation. Now, why is that? Why do you think this is that way? Why would current vary? Any idea? Sorry? That's right. There's a clock. Right? So you have your circuit sitting there. It does a bunch of computation. Your clock comes in and says, okay, do some stuff. And everything starts going back and forth and back and forth, do a lot of stuff, and then it goes in equilibrium again. And we cannot do anything before the system goes in equilibrium. You don't want to have the clock to hit while you're still doing stuff. So it goes in equilibrium, very small current. Then the clock hits again, bingo, you get more current. So that's why we call this the instantaneous power dissipation, is this IT times VDD. Now, why is this important? Well, for instance, the peak current here that I'm carrying is something I have to provide. Right? If for instance, I have a thing has an instantaneous power of 100 watt, and I have a supply voltage of 1 volt, it means that my current can be 100 amps. Right? 100 watt chip, I have 1 volt supply, my current will be 100 amps. 100 amps, for those of you who ever played with circuitry, 100 amps is a lot of current. Huge amount of current. And if you take a tiny little wire and I try to get 100 amps to this thing, you blow it away. It just evaporates. So obviously the peak current will determine how we have to size the wires to make sure that I can get that current into the chip. We have to be very careful with that. Okay? So that's why peak current is important. Peak power or instantaneous power is helping me to size up my power network in such a way that I can provide the right current at the right time. But in general, though, we're more interested, another reason why power is important, as I mentioned, is that chips get hot, right? Power dissipation, if you have increased power dissipation, chips get hotter. Just put your laptop on your lap for a while. It's called a laptop, but it's actually very hard to keep it on your lap for too long a time because it overheats, your lap at least. Actually, this is heat. The heat or the temperature of your chip typically is not going to be a function of the peak power or the instantaneous power, but of the average power, right? It's how much do I use on the average. So what we're going to do, the average power here, which is a more important metric, is you take your instantaneous power dissipation and you average over a certain period of time, T, capital T, whatever it is. So we integrate this thing, and you can see that the average power is V supply over the period of interval of interest, and you take the integrated value of your supply current. Okay? So that's an important parameter because P average, think about it, P average is going to be proportional to the heat that you take basically out of the chip. And it's basically dissipated, turn into thermal type of effects. Now, there's some other important metrics. In a mobile application, I have a battery, right? My battery is going to drive my device here. And obviously, power is an interesting thing to know. But actually, if I have mobile application, I don't really care that much about power. Because a battery stores an amount of energy, right? I have charged it up, and there's an amount of energy. The time I'm going to be, or the length of time of computation I can perform out of that single battery might be determined by the average power, but more importantly, I think it is determined by energy. How much energy do I use to compute a certain computation? Right? So the subtle difference here. Power is the amount of energy I compute per unit time. Energy itself is a metric of the amount of basically the amount of work I can do. Right? It doesn't say how fast it is. If I do things slowly, I could actually, with the same energy, I can go a lot longer. Right? If I basically reduce the average power dissipation. So energy is not a very important metric, and which one is important depends upon the application at hand. If I'm, for instance, in a data center, like Google, where there's a lot of computation, I'm going to be concerned about power. How much power do I draw? Because that's going to determine how hot my room is going to become and how much air conditioning I have to put into place. For a laptop, I also might be concerned about power a little bit. It's going to determine how much fans I have to put in my laptop. But another concern, let's say for cell phones and also for laptops, I go on a plane, I have an overseas trip of 8 hours. Will my computer last for 8 hours? Right? That's determined by the energy utilization. How much energy do I have in my battery, and how much does it cost me to perform a certain computation? So all those metrics are important, and it really depends upon the circumstances, if it's going to be power you're going to be looking at, and energy. Now, here's an interesting statement. So typically in a design, what I would like to be fast, and I would like to have low power. Right? Seems to be like an obvious thing. So delay is Tp. I have figured out how to compute my average power, P. So you want to get both, right? Low power, low energy, low delay. If you multiply the two together, P times Tp, you take the propagation delay of your gate and you multiply it with the average power dissipation of that gate, you get something which is called the power delay product. Because it seems like an interesting metric, right? I want to get power small, I want to get energy, I want to get delay small. If I multiply the two, that seems to be something you want to minimize. Turns out that this power delay product you look about this is watts times seconds. Watts times seconds is joules, I hope. So it's an energy metric. Basically, it's a metric of the energy efficiency of a gate. So power delay products, we'll come back to that. The first thing you do when you compute a gate, you're going to compute its average power dissipation, you're going to compute its delay, you multiply the two together, and you have this power delay product. It's a quality metric of a gate, put it this way. And as I said, it's per definition energy. But remember energy, if I just would minimize energy in itself, it turns out that you want to minimize energy, we'll come back to that later, it'll become obvious that if I want to minimize energy of a gate, actually the slower I go, the better it will be. If I really want to make something that is ultra low energy, I want to make it very, 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 very slow. So this is an interesting method, but optimizing for just say I want to get the minimum power delay product might not be the right thing to do. So some other people say, well, gee, I like to have low energy, but I also like to have high performance. So they have another metric defined, which is called the energy delay product, where you take your power delay product and you multiply by TP. Or it's energy times TP, or it's basically equal to power times TP squared. So you put some more emphasis on the performance. Because in pure energy, as I said, you want to go to low energy, you make it slow as possible, you reduce the supply voltage as far as you can. It's not something you might want to have, let's say, for high performance computing. So there's some different metrics we're going to play with in design. But remember, average power, peak power, power delay product, energy. These are the 4 metrics we're going to be looking at. And we're going to compute all of those. Okay. So let's do an inverter. Look at an inverter, let's say a capacitor. A typical model here, your inverter. Remember that I can model my inverter as a resistive capacitor network. Because just for propagation, if you look at a CMOS inverter, I can model it as like a network like this. What I do is I charge up a capacitor through a resistor, or I discharge a capacitor to a resistor in the other direction. This is the first order model of an inverter. Okay? You charge up or you discharge to a resistor. So the question I'm asking myself is, how much energy does it take you to do so? It's a good question, right? So I have my inverter. How much energy will I consume to charge up and discharge this capacitor? Well, let's take the low to high transition. Initial value here is 0, and we're going to go to VDD. Right? We're charging up the capacitor from 0 to VDD. How much energy does that take from the supply? Well, if you think about it, the capacitor initially has 0 charge, and the end has CL times VDD charge stored on it. Right? That's the definition of charge on the capacitor. The definition of capacitance is basically Q is equal to CL times VDD. Now, how much energy does that take? Well, it's basically equal to Q times VDD. Again, something you have learned in E40. You work all this thing out, you see that the amount of energy I have been taking out of the supply to charge up this capacitor to the charge Q is CL times VDD times VDD. Right? My charge is CL VDD. I'm taking this out of the supply at VDD, so I get CL times VDD times VDD. That's my energy. Or it's equal to CL times VDD squared. Okay, that's the easy way of deriving it. If you don't believe me, or if you got part of 40, I'm going to convince you. I actually can do this, I can prove this by just doing some simple analysis. So let me take the same circuit again. Here's my input. I'm going to step this up. This is going to go from 0 to VDD. So how do we compute the energy? Well, remember, the energy is the integration over the power dissipation over time. Right? So we take, for instance, let's say I have a 0, 1 transition. I'm going to integrate the power over the period 0 to t, where t is the interval it takes to get this whole thing charged up, which could be infinitely long. Okay? So let's say you might say this is 0 to infinity. Okay? Now, PDD, what I'm taking out of supply, the power of the supply is going to be VDD times the current flowing out of the supply, IDD, and as I said, this is a variable current. Your charge is going to go up, so your current, this is your V out. You know, the current is going to be very high initially, and then slowly but surely is going to go to 0. Okay? Now, IDD, I have an expression for that. IDD is equal to CL times dV out dt. Right? I plug this in this equation, and I get now a new form of my integral, which is that the energy from 0 to 1 is equal to VDD times the integral from 0 to VDD times CL dV out. CL goes out, and bingo, I get the same number, CL VDD squared. So when I charge up a capacitor, I take out of the supply a total amount of energy which is equal to CL VDD squared. Now you might ask yourself is what happens with that energy? So the supply is sitting there, and you take energy out of the supply, out of your battery, let's say. Where does it go? That's a good question. Well, let's figure out at the end of the period of time, we're charging up this capacitor, how much energy is stored on the capacitor, right? Well, it's quite simple. I can compute this again, but instead of using the power taken from the supply, I take the power basically on the capacitor. There's one subtle difference. Instead of using VDD here, it's V out times IL. So it's V out is the voltage, and IL is the capacitor flowing, the current flowing to the capacitor. You write this out, and you end up with a equation which says that the energy stored on the capacitor is equal to half CL VDD squared. Very interesting. I take CL VDD squared out of the supply, and half and that's up on the capacitor. So what happened with the other half? Where is it gone? Yes? No. No. Good try. Where did it go?
Gets dissipated in the resistor?
That's right. So this current flows to the resistor. When current flows to the resistor, you get power dissipation as well. It basically, and what the resistor does, it turns this the energy they take from a battery, it turns electrical energy into heat. Right? It basically becomes thermal. And that's why your laptop heats up. Every time I do a transition, I basically turn electrical energy that I have stored into heat dissipation. And the interesting part is it's actually equally divided between the two. Half goes on the capacitor, half goes on the resistor, independent of the size of the resistor. If you make this a big resistor or a tiny little resistor, still the same thing, because there's no resistance popping up here at all in this equation. It's only dependent upon the size of the capacitor and VDD, obviously. And even more importantly, it's quadratic in VDD. So you might already start imagining now why we would like to reduce the supply voltages in circuits. If I reduce VDD with a factor of 2, my energy goes down with a factor of 4. That's a good gain. That's why we don't run things at 12 volts anymore. Well, there's other reasons as well, but it's one of the good reasons. Okay? So that's an interesting observation. So that's now what's happening in the charge up cycle. What's happening in the opposite cycle? When I discharge the capacitance, what I take is I take this charge, basically, and I now going to have current flowing the opposite direction. Right? I basically take the capacitor and I discharge it to 0. In the end, 0 volt over the capacitor. So all that energy is gone. There's nothing on the capacitor anymore, right? There's no charge anymore. So where did it go? Well, again, it got dissipated in the resistor. So in the next cycle, so half of the energy gets basically consumed while you're charging up the capacitor, and then you turn it back again into heat when you do this discharging. And then all energy is dissipated. Okay? So, but remember those numbers, they're quite important. Okay. Good. So now we know how to compute propagation delay. We know how to compute energy. Let's try to do an inverter, a real inverter, and see where it comes from, why I believe that this is a single RC network. Well, let me do a very simplifying type of analysis of a transistor. This is absolutely simplifying. I'm not going to basically come up with complex equations yet. We'll do that next lecture. But let me take my first shot at a transistor. Well, transistor to me, from a digital world, this is an NMOS device, has 3 terminals, or actually 4, source, gate, and drain. And we'll add one more, which is called the bulk, but I'll ignore it for the time being. But so it's a 3-terminal device with 1 control terminal and 2 input-output terminals. Right? Now, in the analog world, transistors can do a lot of things. It provides gain and all this kind of stuff, has GM and all this kind of nice things you can play around it. Digital world, life is a lot simpler. If I look at a transistor, what I think about first is, what a transistor is a switch. Simple switch that you have a certain voltage in there, which is called the threshold voltage. And if my gate source voltage is higher than threshold voltage, I turn the transistor on. I consider this a switch that's being closed. And when my VGS is smaller than VT, my switch goes open. So it's a very simple switch model. Now when it's closed, obviously it's not a short circuit. It actually has some on resistance connected to it. Right? And there's still, you have a channel here, current flow to this channel has resistivity connected to it. So But in the first shot, this actually is just fine. For a lot of digital circuits, if I want to understand how the system works, this is more than enough from a functionality perspective. Transistor as a switch. Now, with purely a switch itself, it's kind of hard to build good circuits. There actually turns out that in our MOS process, we have two types of switches, which is kind of nice. They're complementary switches. I have one device. Let me go here. Oh, this is the same thing. It's just repeating what I just said. Here's your switch. VGS smaller than VT, switch is open. When VGS is larger than VTH, the threshold voltage, the switch is closed, and we have an on resistance of equal to R on. Right? And as I said, we have two types of switches. We have an NMOS device, and fortunately, we have another device which is complementary. And complementary means in the following thing. It's basically this PMOS behaves in an inverted fashion. Actually, when VGS is larger than 0, let's say you have no threshold here. Let's assume that threshold is close to 0. When VGS will be larger than 0, the switch is going to be, in that particular case, open. And when we drop VGS below the threshold voltage, or make it or below 0, let's say, make it negative, we're going to close the switch. Here's the opposite. You have to turn it on. You have to have a VGS larger than 0, or VTH. Assume that VTH is close to 0 right now. When you want to turn it off, we apply a negative voltage, or 0. Here, the opposite thing. When you want to turn it on, you basically have to apply negative voltage. Okay? Just the opposite behavior from each other. And that's the beauty of those things. Now, we basically can implement a circuit by putting two of those switches on top of each other. And, oh yeah, I think, let me skip that for the time being. Let's go to an inverter. So, what we do with a CMOS inverter is exactly what I just said. You take a PMOS device, right here, and you stack it on top of an NMOS device. Okay, connect them together, and somehow we have some capacitance at the output. We'll come back later about where that capacitance comes from. But in a sense, what I have here now is two switches on top of each other. So you have a PMOS switch, and you have an NMOS switch. And that's my output. And you have a capacitor. This is VDD. This is 0. And now I apply the same input, Vin, to both. Now, these are complementary switches, which means that if Vn is large, is high, what's going to happen is that I'm going to turn on this device right here. I turn on the NMOS, and I turn off the PMOS, because they're inverting elements. On the other one, Vin is low, I turn on the PMOS, and I turn off the NMOS. All right, so you have two switches on top of each other, and in steady state, you either have one turned on, the NMOS, or the PMOS. Never both at the same time in steady state. And as a result, you can see that, for instance, if I turn on only the NMOS, the PMOS is off, so you have an open switch. This is on. What you really have is an equivalent network where you have Rn and Cl, or this resistor is going to discharge your capacitor 0. Bingo, my output is going to be 0. Is on the other hand, the PMOS is on, and the NMOS is off. I'm going to get Rp, VDD. You can see that I'm going to charge up this capacitor to VDD. Okay? So the switch model basically allows you already to kind of understand the basic behavior of an inverter. You don't have to know much more. And actually, if I assume that this model works, that I said, well, gee, I have a transistor with an on resistance R on, and an open circuit when it's off, I actually already can compute all the important parameters that we were concerned about. Actually, I can compute the VTH approximately. I can compute propagation delay. I can compute power dissipation. All from this very simple network. Now, it's a simplification, right? Be aware of that. We'll come back to that later. This idea of having a fixed resistance there, which is a linear resistance, yeah, it's nice, but it's a first-order approximation. You will see in real transistors that the resistor kind of does weird stuff. It changes over time. It's not a constant, right? And the idea that a transistor is an ideal switch when it's off, is an open circuit, it's a little bit illusionary as well. So life is going to be a little bit more complicated than that. But in general, though, this holds. It really means that I can do a lot of analysis just thinking about transistors as switches. Okay? So let's think about propagation. Well, let's think about VTC first. If you look at this model, and say I have a CMOS inverter, I want to find the VTC. Now remember, the VTC has a number of parameters, important ones. VOH, VOL, VM, the gain factor in the middle, and your overall VIH and VIL, because that will give you basically the noise margin. Okay? So let's see how close I can get, or how much I can find out about my gate by just using this simple switch model. Let's first think about VOH. What's the high value from the output for this particular gate? What do you think? If I just look at this switch model, what is going to be VOH, the high value or the value equal to 1 at the output of the VTC? VDD, right? Because what I have is the NMOS is totally off. It's just the PMOS connected. The PMOS is going to charge up this capacitor all the way up to VDD. Bingo. I get basically a VOH equals to VDD. Similarly, we can figure out what VOL is. That's a very nice one as well. VOL is going to be equal to what? Ground, right? You have an NMOS device discharging your capacitor all the way down to ground. So that's already very nice. It means that my voltage swing, the difference between a 0 and a 1, is going to be a complete supply rail. It's going to go from ground to VDD and back, which probably means already that you're going to have some decent noise margins, right? Because I don't give any of my voltage away. I use everything for differentiation between a 0 and a 1. Okay, VM. Any idea what would impact VM in this particular case? The middle point. What would I have to do? Remember, I would like to have VM in the middle. Okay? I would like to be at VDD over 2, because then the chances that I'm going to get a high noise margin on both ends is going to be approximately equal. So what should I do if I want to have a VM in the middle? What's going to determine VM to a certain degree, first order degree? So remember, VM is when we have an input voltage which is not high, it's not low, but in the middle. We apply VDD over 2 at the input, let's say, right? Or we do this. We connect this to that. That's really what I do, right? That's the way we determine VM. We take the input equal to the output. You're going to be somewhere, you can imagine that in that operational mode, both transistors are going to be on, right? You're somewhere applying in the middle. The PMOS is going to be on. The NMOS is going to be partially on. So let's assume that you get something like this. Both switches on at the same time. So you have RP, you have RM. So what do I have to do to keep VM in the middle? Approximately. That's right. You want to make sure that your transistors, that the resistors are approximately the same. In the middle region, you want to make sure that your PMOS has approximately the same resistance as your NMOS. That's an important thing. The balanced design is going to try to do is make sure that your transistors are sized in such a way that you get identical driving strength for both your PMOS and your NMOS device. Now, you may remember from 105 that that is not naturally the case. If I take the smallest possible NMOS, and I take the smallest possible PMOS, you will see that your PMOS is a weaker device, right? And it has less driving current, because it basically uses holes, and holes basically have a lower mobility than electrons. So what we're going to have to do to create a symmetrical gate is we're going to have to make our PMOS a little bit stronger. How do we do that? Well, we increase the size of the PMOS. So typically in a CMOS inverter, the PMOS is going to be about double the size of the NMOS. Right? And in this case, I'm going to make the driving strength of both the same, and then you can see this resistive divider is going to be equally balanced. And my VM will end up in the middle. Very first order. Right? We're going to do more complex analysis of this later, but you can imagine that if the devices are equal strength, you will see a more symmetrical characteristic than when one device overpowering the other one. Okay. Now, you can do other things. Now, so this is my first order analysis. We've seen that. And I mentioned this, that your VM is a function of the ratio between Rp and Rn, as you can imagine. This is actually a simulated characteristic. Now, you can see that I should be able to compute the gain here in this point. Right? If I put my inverter, not with my first order switch model gain capability, but if I would know the gain in the middle, I can do some first order analysis of where VIH and VIL are going to be. I'm going to stay away from that. I think with the first order switch model, it's very hard to compute exactly what the noise margins are going to be, because I don't really have enough understanding of what's going to determine the gain in this mid-region. I'll come back to that later. You need a little bit more complex model. But this is a simulated inverter using SPICE. We take a CMOS inverter, you simulate it, and you can see this is pretty nice. My midpoint is about 1.25 volt approximately. So, hey, it's kind of nicely balanced. You can see this very symmetrical characteristic. You can see that if I look at VIL here and VIH here, you see they're darn close to VM. It's not infinite gain, but you look at this thing, this has darn good gain in the middle point. So if I would have the ideal characteristic, would be like this, like this, we see it's very close to each other. They approximate each other very nicely. That's why CMOS inverters are good inverters, solid inverters, because they really have almost the ideal voltage transfer characteristic. And you want to know the numbers. This was for a 250 micronanometer technology with a 2.5 volt supply voltage. You can see VOL 0, VOH 2.5 volt. VM was not perfectly 1.25 volt, was 1.2. And if you compute the noise margin, you can see that noise margins high and low are 1.0.5 volt, which is large. Given the fact that I have only 2.5 volt supply, the transition region is only going to be about 400 millivolt. And all the rest is really legal 0, legal 1. That's nice. Again, shows why this is a good inverter. Okay, so we've already derived, by just using the switch model, I already kind of gave you a very clear perspective on what the voltage transfer characteristic of an inverter could look like. Now, if you imagine, deriving the propagation delays and power should be fairly easy now as well, because think about it, when we go from, let's say, low to high, what we do is you have your switch model, the PMOS is on, NMOS is off, we're charging up the capacitance through this RP, so we get a circuit that looks like a resistor charging up a capacitor with the supply voltage at the other side here. This is our first order RC network we discussed before. So what's the propagation delay of this thing? Remember, 0.69. So it's going to be 0.69 times RP times CL. That's your propagation delay of this inverter. Yes?
Is that assuming that there's no delay on the transistor at all, really?
Well, the transistor is this resistor, right? So the resistor represents the transistor in this particular case. So the propagation delay exactly is caused by the transistor. The transistor presents if I would have an ideal transistor, would have basically zero resistance, I would be able to charge up this capacitance in no time. But in reality, what's happening, I turn on this PMOS. Let's say I take a step input function, right? I turn on the PMOS, and the PMOS will basically start charging up this capacitor. And my model here, the resistance is a constant, which is not going to be really true in reality. It's going to vary, obviously. But this is already a pretty darn good approximation. It says, okay, if I would know the average resistance of my PMOS device and know the capacitance, I can compute the 50 to 50% point delay as 0.69 times RP times CL. Okay? Now, in the opposite direction, the high to low direction is the same thing, but it's now an NMOS transistor discharging your capacitance. Again, this is a first order RC network. Propagation delay here, TP, from high to low is going to be equal to 0.69 times Rn times CL. Okay? Same deal. However, if you now look at your propagation delay, you see there's one subtle difference between, it's not subtle, it's actually quite obvious. This is low to high, the other one is high to low. you can see that the time constant here is going to be determined by the load capacitance times the PMOS resistance. In the other case is the load capacitance times the NMOS resistance, right? So you will see that unless I make my devices exactly the same strength, my TPHL and TPLH are going to be different because they're caused by totally different phenomena. Here it's a PMOS charging capacitor. Here's an NMOS discharging capacitance. So now you can understand why the high to low and low to high propagation delays are going to be different. There are different devices creating those delays. Okay? And if you want to have symmetrical, then again I have to make Rn equal to Rp. If you make Rn and Rp equal to each other, then your low to high and high to low transition are going to be approximately the same. Okay? But basically done. If I basically, and actually as I said, that this is a darn good approximation of the propagation delay of a CMOS inverter. The only question that you have to ask yourself is what is Rp and what is CL? And while it looks simple at the first hand, we'll actually spend quite a bit of time to figure out exactly what that CL is. Because that's going to be important, right? Because I want to make a fast gate, what should I do? Make sure my capacitance is as small as possible. And if I want to make something fast, I want to make sure that this is not too big. And the second thing I want to do is make my resistors as small as possible, or the resistance of my transistor as small as possible. So those are the two optimization play as designer. I want to make something fast, small capacitance, small resistance. Small resistance means bigger transistors. Right? You can basically sizing the transistors, you can make something faster or slower. We'll come back to that later. Okay. So CMOS properties, and by the way, this again is my first order RC network. So how much energy do I do here? CL VDD squared, right? Anytime I charge this up, I take CL VDD squared out of the supply. Half goes on the capacitance, half goes into heat in the PMOS device, and then I discharge it. Half what was stored on the capacitance is now dissipated as heat in the NMOS device. Right? So we know that's solution as well. So let me summarize the important properties of the CMOS inverter. Full rail-to-rail swing, which is very important. It gives me a high noise margin. If I make my PMOS and NMOS transistors same, it's going to be symmetrical. The propagation delay is a function of the load of the. Another interesting thing is that I haven't pointed out yet. So I remember the CL VDD squared. Right. Now look at a CMOS inverter in standby. Let's say we have done, the transition is finished. You either at 0 or at 1 at the output. What's going to be the power dissipation, the instantaneous power dissipation of the device at that point in time? It's going to be 0, right? Because what I have is let's say we have the PMOS on. You have capacitance here. This is charged up to VDD. This is VDD. There's no current flowing through this anymore. The NMOS device is supposed to be completely off, so no current flowing through it. So you can see that in that one position, this device is not consuming any power dissipation. It only consumes power when you charge the capacitance or when you discharge it. Then you take power out of the supply. But when you don't do anything, supposedly here you don't consume any power. Same thing with the 0. In the 0 condition, I have something like this. You have Rn and you have CL. This is at 0, no current flowing to this device. The PMOS device is off. So that's a very important property. CMOS inverter, when you don't do anything, doesn't consume any power, at least in an ideal fashion. This is why in 1980-something, early 1980s, people switched to CMOS technology. That's the main reason. Before that, 1970s, all your microprocessors, the 4004, 4040, 8080, were designed with only NMOS transistors. It's a simpler technology. If I don't have to make PMOS technologies, you can imagine PMOS transistors. You can imagine that my process technology is going to be a little bit simpler, less masks, right? So and that's exactly what we did. But there's a real problem if you don't have complementary devices. To create something that has gain, you have to have a load device and a switching device. NMOS transistors only, logic, always consumed current, even when it was not doing anything. So that works when you have only 1,000 gates. But if you start putting at 10,000 gates, all of them doing nothing but consuming power, your power starts to go up and up and up and up and up and up. We call it static power dissipation. Right? So early 1980s, suddenly people said we have to do something different. So we switched to CMOS. Because CMOS basically had complementary devices. You turn on the NMOS or the PMOS, but never both at the same time, unless when you're basically transitioning. Then you have both of them on at the same time. So no static power dissipation, which was a big feature. So it was very clear in 1985, approximately, people said, hey, we solved the power problem. Done. We use CMOS, never any power problems anymore, ever. Lasted about 10 years. Because number one, is circuits start to switch faster. So the dynamic power dissipation, the power it takes to charge and discharge capacity became bigger and bigger and bigger. And there's another thing which is important and which I'm going to briefly illustrate now, is that modern transistors actually take some of those gains that we got by adopting CMOS design. And let me show you that. So this is your transistor in sub-100 nanometers. Remember, the ideal transistor, when it's off, it's off. It's an open circuit. When it's on, it has a certain resistance. In reality, the world is a little bit different now. When it's on, it still has non-resistance, R on. But when it's off, it's not really off. It's like a switch that I tried to close, open up, but there's still some resistance sitting in between the two, a fairly large one. We call this the off resistance. Now, obviously, they're not the same. If I would the same, it wouldn't be a switch anymore. They wouldn't do anything. There's about 3 to 4 or 5 orders of magnitude the difference between those two. Okay? So you might say, well, that's the ideal device. I think probably more like 3 orders of magnitude is a good number to think about. So factor 1,000. So your on resistance is about 1,000 times smaller than your off resistance. But let's think what this does to your voltage transfer characteristic and your device parameters. Okay, let's reason about this a little bit and say, okay, instead of having an ideal switch, I have a somewhat degenerated switch, as we see in modern CMOS technologies. So let's first think about reliability. Think about VOH. If I know I would have I want to sketch my high output voltage. Well, obviously, to get a high output voltage, I apply a small input. My PMOS goes on. My PMOS is on. NMOS is off. So what I'm getting here is on. Right? The on resistance of my I have a capacitor here. Doesn't really matter. Now, for the NMOS, in the other case, we assume that it was an open circuit. There was nothing there. In reality, now you get something like this. It's RN. Off. Okay? So what's now going to be the voltage of VOH? In the past, it was exactly equal to VDD, right? Because you just charge up the capacitor all the way up to the supply rail. Here you can see that under this condition, steady state, you forget about the capacitor. Well, this is a resistive divider. And my output is going to be equal to VDD times RP on. At least you should remember that, right? How to solve resistive divider. I assume you know that. The first, I think, thing that you learned in 40. Now you can see if there's 3 orders of magnitude away between R on off and RP on, this factor becomes fairly small, and we still assume that this is close to VDD. But it's not exactly VDD anymore. Right? It might approach it, but it's not exactly. So you can see if R on off starts to get smaller and smaller, you get lousier and lousier transistors, you will see that VOH is not going to be exactly VDD anymore, but actually starts dropping a little bit below it. Same thing is true for the zero voltage. It's just the opposite case, right? In that case, I would have RP off, and this is RN on. And it's going to be the voltage VOL is going to be equal to RP off, RN, what did I say here? This is wrong, right? Yeah, I don't know how to solve my, oops. This is RP off. Rn off over Rp on plus Rn off, obviously, which should be equal to 1. In this case, it's Rn, it's basically Rn off, let's see, where am I now? Here. It's Rn on over Rp off plus Rn on, obviously. Oops, I should go back to 42. But you can see here in this case, Rn on is very small, Rp off is very thin, basically goes down to 0. This factor is small, it's approximately equal to 0. Okay? But it's not exactly equal to 0. So we get some degeneration of our voltage levels as a result of non-ideal transistors. Now let's think what it's going to do for propagation delay. So I want to charge up a capacitor using, and turn on my transistor. So I have Rp on and I have Rn off. Right? I'm going to charge them up. You can see that your time constant becomes a little bit more complex. But again, this is a very large resistance compared to this one. It might degenerate your delay a little bit, but not by much. Because you can see not all current is going to flow into the capacitor. Well, actually, some current actually will flow to this resistor here. I'm not going to use some of the charge to charge up the capacitor. I'm losing some to that non-ideal NMOS device. So it slows down your network a little bit. Not much, but a bit. Right? So that's not a big factor. So the fact that we have some leakage, by the way, that's what we call it, leakage happening to the transistor which is off, is going to degenerate your propagation delays a little bit as well, but not much. Not a big factor. Where leakage really is going to matter is in the power dissipation area. Because now, if you look at power and energy, the ideal case of a CMOS inverter, you have power dissipation equal to CL VDD squared, dynamic power dissipation when you're switching. I take an amount of energy E CL VDD squared out of the supply every time I charge up my capacitor from 0 to 1. Right? Now, what's going to happen in this case here? Well, what we see is that in steady state, when I'm not doing anything, suppose this is equal to 1. Right? So you have VDD, the output is 1. So this is going to be equal to Rp on. This is going to be equal to Rn off. Okay? Now you see that in steady state, even if I'm not doing anything, current will flow to this resistive chain. Leakage current. It's not big. It's actually equal to VDD over Rp off, Rp on plus Rn off. That's really going to be my current. And I want to multiply. I want to figure out what the power dissipation that is. I multiply this with VDD. So P is equal to VDD squared times over Rp on plus Rn off. So you can see that actually some major current is going to start flowing. Or that's not major. It's actually fairly small, but current is flowing to the device. And you see that power is being dissipated when I'm not doing anything. Static power dissipation. Actually, since Rn off is going to be much larger than Rp on, you can eliminate that. You can see that the power dissipation is going to be equal to VDD squared over Rn off approximately. Right? Now you say, well, this is very small. Remember this 3 orders of magnitude to 5 orders of magnitude? My resistance here might be, the current flow in this thing might be the order of nanoamps. Let's say nanoamps to about, it's definitely, let's say 1 to 10 nanoamp. That's small, right? 1 nanoamp times 1 volt. That's 1 nanowatt. It's not huge. So you say, why bother? Why worry about this? Well, the fact is that in a current chip today, the most advanced chips, we have probably maybe a couple of 100 million gates sitting there. If you have 100 million gates, that's 10 to the 8 times 1 nanoamp, that's 10 to minus 9, is 0.1 watt. In reality, this is very often higher, and this might be higher as well. So in that case, we actually might see that you can consume watts of power dissipation by doing nothing. That's a pain, because I don't want to have a cell phone sitting there, and while basically there's nothing happening at all, the thing just drains the batteries, right, by doing nothing. And that's a big problem. Something that has emerged as one of the bigger problems in design today is this static power dissipation. The problem that we solved by going to CMOS is actually slowly but surely coming back again. And we'll talk more about that later in the semester when we talk a little bit about power. But you have to see that devices are not as ideal anymore as they used to be. Okay? And again, there's an awful lot you can learn by just thinking about transistors as switches. And we'll do this very often. It's only when you really want to get precise information about gain factors and where the capacitors are and so on and so forth that you have to play with this factor. Okay, so I have about 50 minutes. And what I'm going to do in the next 15 minutes is start to talk a little bit about process technology. We have actually, before we go to transistors, I think it's important that you understand a little bit how those transistors are being made, because it's very important. I think, and the main reason for that is that you have to understand, I think what you want to, obviously this is not 143, this is not 130. I don't think for this class you have to understand exactly what the band gaps are and how they all get together and things like that, exactly what the physical mechanisms are, or exactly how you manufacture every particular step in the process technology. But it's important to have an intuitive perspective on a transistor. Because if I'm going to say, well, gee, you have gate capacitance. If you don't understand where that gate capacitance comes from physically, it's kind of hard to understand how you can optimize a design, a layout, to understand how to minimize, for instance, gate capacitance. So some perspective on how a device looks like in a 3D fashion is going to help you to kind of understand a little bit how you can manipulate sizes of transistors or certain other parameters of a transistor to get a better design. And that's why I think it's important to get at least some perspective on how CMOS transistors look like, and also importantly, how they're fabricated. It also helps, the fabrication process also helps you to understand a little bit how the whole flow of things works. Basically, why we can make things of about a couple of millions of transistors or a billion transistors on a single die. Actually, next week, I think in ISSCC, next week, Monday, Tuesday, Wednesday, we have the biggest circuits conference in town in San Francisco. Every year, there's a conference there. The newest circuits are being introduced. And I was just looking at some of the early press releases, and Intel will announce probably the biggest chip ever built. It has, I think, about 2 billion transistors on a single die. Quad core. It has 4 processors on a chip. A couple of billion transistors. That's a huge number. Now think about it. How can you print those things all reliably? Billions of that. That's 2 times 10 to the 9. Huge number. So all of this is really due to this factor here. That the fact that we have come up with a manufacturing process that allows you to print reliably so many transistors on a single die over and over and over again. So let me kind of point out a little bit how this is done. I think it's kind of interesting because for those of you who have not taken 143, probably have not seen this, but it's actually worthwhile to understand how things are the way they are. You've definitely seen this. This is a 3-dimensional picture of a NMOS transistor. Right? So the way we basically make a transistor is somewhere we have a slice of silicon, right here, which we call the substrate. Substrate is silicon, as I showed you, there's a wafer, and typically the wafers come already with a certain set of impurities in there. Like, for instance, we have a p-type wafer. It means that the basic silicon, your substrate, is already doped with p type of impurities. Okay? Now, to make a transistor, we have to do a couple of things. First of all, we have to have a source and a drain. Source and a drain are basically diffusions, N plus diffusions. You have a gate, and the way the gate is implemented is until about this here, plus polysilicon, with in between there in between the gate and what we call the channel, which is in that substrate material, you have a gate oxide. There's an oxide sitting there. Up until very recently, also this was basically using silicon dioxide. Okay, so you have polysilicon as the gate material, a gate oxide, a drain and a source region implemented as a diffusion. And then what else do we have there? We have some contacts. There's a whole bunch of layers of metallization. Typical process today, advanced process, 9 layers of metal. basically that you can stack on top of each other to make interconnections. Because it's very important, you have 1 billion transistors. If you cannot connect them together, they're useless. You have to connect the drain to the source, and the gate, and whatever to the VDD and supply. So there's a whole bunch of layers of metallization that allow us to connect the things. Again, up to about 5 years ago, there was aluminum. Things have changed. Things actually have been changing quite substantially. Today, more and more we're starting to use copper as the interconnect material, not aluminum anymore. The silicon dioxide gate, as of this year, the most advanced process started using something different, which is called a high-K dielectric. And the newest gates don't use polysilicon anymore, but actually use aluminum or some other metal, titanium or tungsten type of material, tungsten as basically the gate material. So there's new metal gate stuff coming up. It's changing, but overall the concept is the same, just different materials, but source drain diffusions, channel in between, gate capacitance, and a gate on top. And then finally, around your transistor, we have what's called the stopper, basically implants or whatever it is, trenches, things that allow you to isolate one transistor from another one. Because obviously, if I have one transistor here and one next to it, I don't want them to interfere with each other. Current flowing from the source of one to the source of the other one. So that's why we have this field oxide. You put a very thick oxide in between that basically effectively blocks charges to move from one to the other one. Okay? And that's the way we, in a very simplistic way, build transistors. Okay? Now, you can see there's a bunch of stuff to be doing. If I want to manufacture a device like that, obviously I'm starting with a substrate, but then I'm going to go to a set of steps that gradually but surely builds up all those patterns. Figure out where should I have gates, where should I have sources, where should I have drain, where should I have isolation material. Okay? Very complex entity. But the beauty of it, and the absolute beauty of basic silicon manufacturing, is that all those steps typically follow exactly the same pattern. Every one of those things is a repetition of a set of steps. And it's always the same thing over and over and over again. That's the beauty of it. And that's why it's mass producible. It's something that you can understand. You say, here's are the steps, and you repeat them into a row. Actually, this, if you want to know more about it, you want to get all the details on the website of the book. There's actually a whole bunch of detailed steps of how you go through the process. But I'm not going to go to that here. I'm just going to give you the basics. This is, in a nutshell, how you make chips, at least in a simplified format. Okay? As I said, what you do is go to this circle here. There's a circular process, and you go to that circle over and over again. And it takes about 3 weeks to get through the whole process, if you have a good fab. So you have to basically do a whole bunch of steps in a row, 3 weeks to basically make a chip, approximately. So what you do is the following thing. I'm a designer. I'm finished. I put all my patterns down. Say, here's how I want to get polysilicon. Here I want to get diffusion. Ta-da-da-dum, ta-da-da. Right? Figured all of these things out. So I go to the fab. I come up with a big file. They used to put them on tapes. That's why we still call it tape out a chip. You don't bring in a chip or you start processing a chip. No, you tape it out. Typically, you took your design, you put it on a giant tape, and you carried it to the fab. That's the way it worked. So, so what they're going to first do is going to take your patterns and turn them into a set of masks. Masks are pieces of glass material. And on the glass, it will be printed patterns that you want to deposit. The patterns, and for every major step, you will have another set of those masks made. Like polysilicon will have a mask. Diffusion will have a mask. Metal 1 will have a mask. So you have a set of masks, about 25, 30 for a typical CMOS process. And what those glass are, basically, it's like a picture almost. You print on that glass the patterns you want to see repeated. Okay? So it's kind of like an imprint. You make one mold, and you're going to use that over and over and over again to make many wafers. So how are we going to use this? Well, the first thing you do, let's say, suppose I want to build a silicon dioxide. Let's say a gate oxide. Right? So remember the gate oxide, silicon dioxide. What you take is take your substrate, and I put it in the oven for a while. At a 400, 500 degrees Celsius, something like that. And you basically put oxide in front of top of your silicon. What's happening? Silicon dioxide will start to grow. Okay? So I put a thin layer of silicon dioxide all over the chip. all over the wafer. The whole wafer is coated exactly with the same thing. No patterns yet. So how do we pattern it? Well, what we're going to do is something which is very similar, extremely similar to basically the good old photographic process. It's good old because everybody makes digital pictures these days, so nobody uses film anymore. But it's the same type of concept of film. On top of that silicon dioxide now, I put on another layer which is called photoresist. It's a material that's sensitive to light. If it sees light, it might harden. The part that doesn't see light basically stays soft, for example, an example, right? Or vice versa. There's two types of resist. So we coat the whole wafer with that resist, and now I put this thing in together with the mask in a very expensive machine which is called a stepper. It's one of the most expensive pieces of equipment that you have in a fab today. And they're getting more and more expensive every day. A big cost part of the fab cost. So what you do, you take your wafer, you put the mask on top of it, and you shine light on it. Not normal light, but light with very short wavelengths. You shine it on there, and you can imagine you have patterns on your glass, and some parts of your wafer will be exposed to light, some parts will not be. Right? So you make an imprint of, you take that mask and you print it on top of that wafer. You take the wafer away. Now some part will be, as I said, some has seen light, basically might get hardened. Other part basically remains soft. Then we go to a step which is called photoresist development. We put some other liquids on there that basically extend that process. Really says that's part of basically what's seen. Silicon is now going to become that's in light is going to be resistive to some etching. Other part will become sensitive to etching. So that's basically like you go in the dark room and you develop your picture. Right? It basically takes that process, what you basically put on the film, and hardens it and make sure it doesn't disappear. Then we're going to basically take this thing to an etcher. An etcher, and there's different types of etcher. We have what's called liquid etching. You've heard about etching before. We use it to make artwork. Take a piece of metal, you put some very vicious type of chemicals on it, and it eats it away. We do the same thing for chips. Actually, in some of the fabs, we're using some very vicious type of materials and for fluids and so on and so forth, things that you don't want to touch from a long distance. Or the other thing is basically you can do dry etching where you basically use plasmas to basically eat part of that thing away. But the bottom line is the same thing. The part that was developed might become insensitive to the etching. The part that was not developed will be sensitive, and you will eat some part of the material away. Then, once I've done that, you etch it for a while. What I've now done is I basically turn that pattern, and I basically, for instance, remember I have my silicon dioxide and my photoresist? I've taken some of those things away. So there's silicon dioxide still left in certain areas, but it's totally removed in other areas. Then I do some cleaning. I get all the crappy stuff out of there. And we're ready to basically, we do the photoresist removal because you want to get all the stuff that you don't use anymore, you take it away. And I go to my next step. I say, okay, now I've done silicon dioxide. Maybe now I want to do diffusion. Same thing, you take your patterns, you put your patterns down, you remove basically some materials, and then you put it on a diffusion machine. Say, I'm only going to get diffusion in certain areas. And you do this over and over again. So you can imagine that this lithography part is a very important component of chip making. It's really that thing that allows us to take a single pattern and repeat it hundreds of times over a wafer. Or we basically can do billions of transistors in one single shot by just shining light on it. We transfer everything to a wafer. And then the same mask can be used again for the next wafer, and the next wafer, and the next wafer. So we have to make masks only one time to transfer many, many, many times to different silicon wafers. Now, as I already mentioned last class, masks are not simple anymore. They used to be simple. I could do this in a little dark room, and we made our own masks. Not anymore. Oops. Well, my computer decided it's almost time for the end of the lecture on its own. That's a very clever computer. But today, masks basically cost you a couple of $100 million for a set. Sorry, a couple of million. Yeah, I said a couple of $1 million, right? Yeah, a couple of million, not $100 million. A couple of $1 million for a set. So, but it's important that you understand that process because I'll show you some example of how we're going to do this in reality in the beginning of next class. Okay? Yes.
I missed last week on Friday's lecture,
Right.
and I wanted to change sections.
Discussion session or lab? What you just do is show up in time, show up at the lecture, the discussion, the lab where you want to be belong to, and there shouldn't be a problem getting there.
Okay.
So just show up at the one, and we're going to take a attendance list at the first lab session. Then we know exactly who's